This topic is called Basic Trigonometric Equations. And the good news is that we've actually already done some of these. There's an example at the beginning of the section in the textbook that says 2 times the sine of theta minus 1 equals 0. And actually, we already know how to solve an equation like this. Add 1 to both sides. Divide both sides by 2. Now, the next, I think, most natural thing to want to do is to take the sine inverse of both sides of this equation. Let's go ahead and do that, and then we'll talk about the implications there. I'm taking the sine inverse of both sides of my equation. Sine of theta equals 1/2. Well, the sine inverse of the sine should just be theta, as long as we meet the criteria that theta is somewhere between negative pi over 2 and pi over 2, somewhere in quadrant 4 or quadrant 1. The sine inverse of 1/2 is an angle. It's the angle whose sine is 1/2. Let's go to quadrant 1 first and recognize that the angle whose sine is 1/2 is the angle whose opposite is 1 and whose hypotenuse is 2. And there's certainly one of these in quadrant 1. Is there one in quadrant 4? Well, no, because there, my opposite would be negative 1. So I'm not going to get another solution for this equation in quadrant 4. But I can use my knowledge of where the sine of an angle is 1/2 to evaluate the right-hand side of this equation as pi over 6. The sine of pi over 6 is 1/2. Therefore, the sine inverse of 1/2 is pi over 6. I haven't been told here whether I'm working in radians or degrees, so the other way to write this would be as 30 degrees. I'll just leave that there in parentheses for now, since we haven't been told what unit we're in. Now, the reason I used sine inverse of sine and sine inverse of 1/2 in this step here was to remind you, first of all, what the sine inverse is, because we're going to be seeing that a lot, and also to remind you that that sine inverse has restrictions on it. We can only deal with sine inverse if we're in quadrants 4 or 1. The thing is, we're not asked to treat this like a function. We're told it's an equation, but it's not necessarily a function. So we actually want all the possible solutions for this equation, not just the one in quadrant 1. If there had been one in quadrant 4, we could have listed that as well. But as it happens, there's another solution in quadrant 2. In quadrant 2, the opposite is also positive. So there's another angle, one in quadrant 2. That's this one here, remember. Not just theta bar or theta prime, the reference angle. So now we want to find what this angle is. The reference angle is the same size. The sine of this angle is 1 over 2, 1/2. So the size of theta prime, or theta bar, is also pi over 6. But the size of this big angle is pi minus pi over 6, which is 5 pi over 6. So I actually have two solutions to my original equation. And in part, that's because I don't have to worry about it being a function. I'm just interested in where the sine of theta is 1/2. Here's another way to look at that. This is a sine graph. There's a place on the sine graph where y equals 1/2. And in fact, as you can see here, there are several places. This goes on forever, of course, in both directions. So what we're doing by trying to solve this equation, which we reduced to this equation here. Let's highlight this version of the equation. I like this one. It's kind of in its simplest form at this point. What we're doing by trying to solve this equation is to find all the places on the x-axis where the y value is 1/2. The first one we run across is pi over 6. The next one is 5 pi over 6. The next one's way over here. After the graph has completed a full cycle, it's just a little bit beyond that. Here's what's happening there. My first solution is here at pi over 6. That's this one right here. My next solution is at 5 pi over 6. That's this one right here. The next one doesn't occur until I go all the way around the circle and come back to something coterminal to pi over 6, and that's this one right here. The next again one would be all the way around past pi over 6 to 5 pi over 6. So now I'm looking at an angle that's coterminal with 5 pi over 6. I can also go in the opposite direction. The first one I'm going to run into there is negative 7 pi over 6. And that's this one back here. There are an infinite number of these because I can just keep going around and around and around the circle as many times as I need to. And whenever I land on an angle that's coterminal with pi over 6, I have a solution. That's this one here and this one here. Whenever I land on an angle that's coterminal with 5 pi over 6, like this one, or even this one back here, that's another solution. And I can keep going forever in both directions. So there's an infinite number of solutions, and I want to be able to find a way to write that as a single or maybe two lines. Instead of writing a list of solutions, I want to write them in as compact a form as I can. So what I'm going to do is, first of all, I'm going to erase my 30 degrees because I've clearly decided I'm working in radians here. There's no context here. This might have been given in degrees, but I've kind of gone forward thinking in radians, so there's no point in having this extraneous notation here. My two primary solutions are theta equals pi over 6 and theta equals 5 pi over 6. I'm going to add to that an expression that lets me add this next solution, the next one, and so on. Basically, I'm looking for angles that are pi over 6 or coterminal to pi over 6. Here's my first one, pi over 6. My next one is going to be pi over 6 plus 2 pi, a full cycle. So I can add 2 pi to pi over 6, and I have another solution. The thing is, I can add 2 pi, or 4 pi, or 6 pi, or I can add negative 2 pi, or negative 4 pi, and I'm going to get another angle that's coterminal here. All of them have signs that are 1/2. So instead of just adding 2 pi, I'm going to add 2 pi k times, where k is an integer, meaning that k can be 1, 2, 3, 17, negative 2, negative 5, or 0. It can be a positive or negative whole number or 0. That's what integers are. Now 0 is an important case, because if k is 0, this whole term is 0, and that's what gives me my original primary solution, pi over 6. If k is 1, I'm at pi over 6 plus 2 pi. If k is 2, I've gone around twice, and so on. So on the graph, this is pi over 6, where k is 0. This is 13 pi over 6. In that case, k is 1. But I also want to be able to do this for when k is 2. Pi over 6 plus 1 times 2 pi plus 2 times 2 pi. And I also want to be able to do it for subtracting multiples of 2 pi. So pi over 6 minus 2 pi and minus 2 times 2 pi, and so on. So this notation lets me do that. Here's my primary angle, my primary solution, and then I write plus 2 pi k. It's easy because now I have all of the solutions that are coterminal with pi over 6. And then I can do the same thing for 5 pi over 6, plus 2 pi k, where k is an integer. This kind of concise, really compact notation is something mathematics is kind of famous for. There are always other ways to write things, but the more precise, concise, and compact it can be, the neater it is and the less room it takes up on a page. Now, part of the reason for this being considered a desirable feature is probably historical. To write this, or to typeset this, would take one set of letters in a printing press. If you were to type out or print out 5 pi over 6, comma, let's see, what's my next one? I'm going to go with pi over 6 because that's easier for me to do mentally. My first solution is pi over 6. My next solution is 13 pi over 6. My next solution is 25 pi over 6, and so on. Now, I've captured in this list the idea that there are multiple solutions, and in fact, by using this ellipsis here, the fact that there is an infinite number of solutions. But there's some stuff missing from this list that's present. Go back up here. It's present in this version of the answer. It looks like they take about the same amount of space on the page, but I'm going to need to include some negative values here. So that's going to make my list longer. Otherwise, it's not clear that I mean that all multiples of 2 pi, either side of pi over 6, are options for my answer. So I'll need to at least include a couple where the solution is negative. That means probably at least 5 solutions. And then the other thing that's clear from this version of the solution that's not clear here is what the pattern is. Here I've made it clear, pi over 6, and then every multiple of 2 pi either side of that. This is clearly one rotation around the circle, starting at pi over 6. So what I'm saying here very clearly is every angle coterminal with pi over 6. That's not clear in this version. So this is the preferred notation, and you'll get used to both reading it and writing it. Now, sometimes you'll be asked for all solutions, and this is how you need to write your answer. In fact, let me put a box around that. This entire thing here is actually the solution to this equation. You need both lines, because without the second line, you're missing half the solutions. All the solutions coterminal to 5 pi over 6. You need both lines, and you can't combine them in any way, because there's no way to get from this angle to this angle and then get around to this angle again by adding the same quantity both times. You're adding a different quantity to get from pi over 6 to 5 pi over 6, then you're adding to get from 5 pi over 6 all the way back around to an angle coterminal with pi over 6. So you need both lines. Let's take a look at another example using cosine. Since we're going to be working with cosine this time, I've created a cosine graph so I can refer to that, and I'm ready to do my unit circle work on a grid here. The thing is, this equation is not in an obvious form to solve using the information that we know. Sure, I could stick it into my calculator, but that doesn't really indicate that I know any trigonometry. Let's do a little algebra first. Divide both sides by 4. That lets me write this as the cosine squared of theta equals 2 over 4, or 1 over 2. Now I'm going to take the square root of both sides. And that gives me the cosine squared of theta equals plus or minus 1 over the square root of 2. That's another way to write plus or minus the square root of 2 over 2. And I don't know which version of these you have in your chart, in your table, or in your experience, but whichever one you're more comfortable with is fine. Now, I've made a mistake here. I took the square root of cosine squared, and I forgot to unsquare. So let me get rid of that. So now I know that the cosine of theta is 1 over the square root of 2, or the square root of 2 over 2. Actually, it's plus or minus that, but we'll start with just the positive one. Where is the cosine of theta equal to square root of 2 over 2? The answer is 45 degrees, or pi over 4. So my first primary answer is theta equals pi over 4. And of course, I can always say plus 2 pi k, where k is an integer. You do need to include this, because if you just say plus 2 pi k, then I don't know what k is. So you need to tell me every time you use it. Now, if you were writing a mathematical paper, then you could include this at the beginning and assume the reader would understand that that follows through the entirety of the paper. If you're really lazy in the case of a problem like this and you just want to write it once, I'll accept that, but I do need to see it at least once. So I have a primary solution. A principal solution is pi over 4, and I can go around the circle, coming back to angles that are coterminal with pi over 4 as many times as I need, or I can go the other way. That's what this plus 2 pi k captures. But that's not the only place where the cosine of an angle is the square root of 2 over 2. Another place is, well, let's see, cosine is adjacent over hypotenuse. And adjacent, in this case, because I'm working with the positive version first, the adjacent side has to be positive. That means I'm on the positive x-axis. The other case that's covered here is negative pi over 4. So I'm going to go down here. I have adjacent, which is still root 2 over 2 over hypotenuse. That's negative pi over 4. There are a couple of different ways to write negative pi over 4. One of them is as negative pi over 4. The other is as, I think I'm going to write the word or here, 8 pi over 4 minus 1 pi over 4, which would be 7 pi over 4. Now, technically they're both correct, but I think I'm inclined, personally anyway, to use 7 pi over 4 because that just tells me it's this angle here. I've started in the standard position and I've gone in a standard direction and I've ended up with this angle here. Negative pi over 4 is coterminal, and so we'll manage to capture it either way when we say plus 2 pi k. K is an integer. We'll capture all multiples of this angle, all coterminal angles, either way. We're either saying start down here and then go around the circle as many times as you need to, or we're saying start by going around almost all the way and then keep going around. If you start by going down first, by going back first, you're starting with negative pi over 4. If you start by going around first, you're starting with 7 pi over 4. Either way, you need to add plus 2 pi k, where k is an integer. Now, that was where cosine is positive. What about where cosine is negative? How did I end up with a plus and a plus or minus in here in the first place? Well, I took the square root of both sides, so I had to include a plus or minus. I've dealt with the cases where cosine is positive. All students take calculus. All ratios are positive here. Sine and cosecant here, I have to think out loud. All students take tangent and cotangent are positive here, and cosine and secant are positive here. So cosine is positive here and here, quadrants 1 and 4. And that's the plus version of this problem. The minus version of the problem is where cosine is negative, which is the other two quadrants. So I'm going to have reference angles in quadrants 3 and 4. I'm also still going to have a ratio of adjacent, root 2, over hypotenuse, 2, except that in this case, my adjacent is negative because I'm on the negative x-axis. This length right here is square root of 2, but this point right here is negative root 2, 0. Let's take a look at what those two angles are. If I start at theta equals 0 and go around the triangle, go around the unit circle to this angle, I'm a certain number of pi over 4s around them. 1 pi over 4, 2 pi over 4. This is 3 pi over 4. So another solution to my equation is 3 pi over 4. Again, starting here, I can go around the unit circle as many times as I need to get additional solutions to my equation. So plus 2 pi k, where k is an integer. Each rotation around the unit circle starting here is an angle coterminal with 3 pi over 4. So its adjacent over hypotenuse is going to be root 2 over 2, negative root 2 over 2. So it satisfies, where am I? It satisfies this equation. So it's an additional solution. 3 pi over 4 is the primary one. 3 pi over 4 plus any multiple of 2 pi, any integer multiple of 2 pi, is another solution. Our last principal or primary solution is this one all the way around here. If this was 3 pi over 4, this is 4 pi over 4, which makes sense because this is pi. One more pi over 4 gives me 5 pi over 4. So my last principal solution is 5 pi over 4. And plus 2 pi k, where k is an integer. Now, I've got here 4 solutions. But in this case, each one of my solutions is exactly 90 degrees around from the solution before it. There's another 90 degrees, pi over 2, right? If we're talking in radians. another 90 degrees, and then another 90 degrees, and then another, and another, and so on. So in this case, I can actually write my answer as theta equals pi over 4, that's where I need to start, plus and any integer multiple of pi over 2, not 2 pi. If I start with pi over 4, which is right here, and I go around pi over 2, that's 90 degrees, I'll get to here. If I go around another pi over 2, I'll get to here. Another one gets me here, another one here, another one here, and so on. If I start at pi over 4 and go backwards, I'll get to another solution that way as well, as long as I go pi over 2 each time. Now, I'm starting at pi over 4, but if I'd wanted to, I could have started at 7 pi over 4. Then I could have gone 7 pi over 4 plus pi over 2 plus pi over 2 plus pi over 2, or 7 pi over 4 minus pi over 2 minus pi over 2, and so on. It's conventional to start with the smallest positive angle. That's why I chose pi over 4 for this answer. But however you decide to write your answer, this conveys exactly the same information as all 4 of these together. I forgot to write here, k is an integer. And that's part of my answer, so I'm going to add that to my little highlighter box. This line here conveys the same information as all 4 of these lines together. So again, this is preferable because it's more compact than having 4 lines together here. We couldn't do that in our previous example because we only had 2 angles, and I can't remember what the primary angle was. I think it was pi over 6. So we had pi over 6 and 5 pi over 6. I can't, with those angles, just go around and then around the same distance again to keep getting new angles. I'm going a shorter distance to get from pi over 6 to 5 pi over 6. To get from 5 pi over 6 to the first angle coterminal with pi over 6, I have to go a much longer distance. So there's no way to write it in a single line. I had to include this angle plus 2 pi k and this angle plus 2 pi k. But because these pink angles are exactly the same distance from one to the next, the gap here is the same size. Because of that, I was able to rewrite all 4 of these lines in this one line here. I didn't use my cosine graph this time, so let me very quickly demonstrate how this all plays out on the cosine graph. Basically, I'm looking for a place where the cosine of theta is equal to this value, positive or negative, this value here. And it turns out that that's at the angle pi over 4. So where the input is pi over 4, which is about here, the output is root 2 over 2. But I want all the x values, or all the theta values, where y is equal to the square root of 2 over 2 or negative the square root of 2 over 2. And that turns out to be, well, this is not going to work very well because I didn't do a good job on my cosine graph. But hopefully you can see that I have values here, 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 and here, and so on. And if I had done a better job on my graph, these tick marks here would be equally spaced, right? And that's this evenly spaced rotation as well. Now you won't always have plus or minus. We didn't have plus or minus on our last example. The plus or minus is one of the reasons that we ended up with equally spaced rotations or equally spaced tick marks. The other was the fact that we were dealing with a multiple of pi over 4, 45 degrees. If you're working with a multiple of 45 degrees, but you don't have a plus or minus, then you're not going to have 4 angles. You're only going to have 2. And so you may or may not be able to write your answer as a single line. There is one other instance, there is one other case, even without a plus or a minus, where you can write your answer as a single line. And we'll take a look at that example next. I'm going to start with a pretty simple one this time. Nothing we really have to work too hard to get into a form where we can solve it for its first angle. I want to solve the equation, the tangent of x equals negative the square root of 3. Well, let's remind ourselves, first of all, that tangent is only going to be negative in this quadrant or this quadrant. And the tangent of x is the square root of 3 when x is pi over 3. So let me erase those marks because those look more like pi over 4 to me. And make my first angle pi over 3 in the second quadrant. Let's see, that's going to be there. This is my reference angle x. And also in quadrant 4, pi over 3, that's my reference angle x. So I've got here, if I make my triangles, two places where the tangent of the angle in question is negative the square root of 3. Tangent is opposite over adjacent. In quadrant 2, I have the square root of 3 over 1, but my 1 is negative because it's on the negative x-axis. The square root of 3 is positive because this line segment, this vertical that I dropped, is parallel to the positive y-axis. In quadrant 4, my square root of 3 is negative because its line segment, its corresponding line segment, is parallel to the negative x-axis. But my 1 is positive because I'm on the positive x-axis. All right, now what I want to know is what angles, all of them, satisfy this equation. We already know a couple of them, although we haven't really identified them yet. Let's start here and figure out what angle this is. Let me use a highlighter, a pen rather, to identify the angle. And then I'll point out that this angle here has a size pi over 3. This angle x bar here has a size pi over 3. Well, if I want to talk about pi over 3's, this is pi, all the way around to here would be pi. So that's 3 pi over 3. And this angle has the size pi over 3. So I'm going to take 3 pi over 3 and subtract pi over 3. That leaves me with 2 pi over 3. So the first angle that satisfies the equation, the tangent of x equals negative root 3, is x equals 2 pi over 3 plus 2 pi k, where k is an integer. The second angle that satisfies that equation, I think I'll use a different color here, is this angle all the way around here. And I can think of that a couple of different ways. If this is 3 pi over 3, this next one here would be 4 pi over 3. This is 5 pi over 3. So my next angle is 5 pi over 3. The other way I could think of this is if this is 0 and this is 2 pi is 6 pi over 3. Subtract one angle the size of pi over 3 from 6 pi over 3 and you get 5 pi over 3. But I still have to write plus 2 pi k, where k is an integer. So I have two solutions to this equation, but I'm going to go back to my unit circle and I'm going to look at how these two solutions relate to each other. Here's my first one. To get to my second one, I have to go around a half circle. So another way to write this solution would be as x equals 2 pi over 3, the first principal solution, plus just pi k, where k is an integer. If I start at 0 and go around to my first principal solution, 2 pi over 3, then I go around pi more, I'll get to the next solution. If I go around pi more, that's 180 degrees, I'll get to the next coterminal solution. Another pi, another pi. So in this case, again, I can either write these two lines or just this one. And writing it as a single line is preferable because it's more compact and easier to read. It also shows not just two isolated solutions, but in a way shows how these two solutions are related to each other. There's a connection here. You only have to go around pi, not 2 pi, to get to the next solution. This two-line answer is not incorrect, but this single-line answer is more concise, more compact, and therefore preferable. Now, I didn't write any instructions on this problem. I didn't have any instructions up here. Solve this for all real solutions. I left that off on purpose because I wanted the first pass at this problem to be another example of the kinds of problems that we've been doing where we find all solutions. But sometimes you're not asked to find all solutions. Sometimes you're asked to find the solutions only on an interval, like 0 to 2 pi. Now, notice that this interval includes 0, so if one of our answers is 0, we need to include it, but it does not include 2 pi. What essentially this is saying is start at 0, go all the way around looking for solutions, but stop just short of a redundant solution, a repeat, a coterminal solution at 2 pi equals 0. In other words, we want all the solutions in one rotation, but by the time we start a second rotation, we want to stop recording answers. So that's a different problem than the one we've just done. In fact, we did all the hard work for this before we wrote our answers in this form. To answer this question, where we're restricting ourselves to the domain 0 to 2 pi, we want to find all the solutions that we run across. Here's the first one, 2 pi over 3. And there's 5 pi over 3, before we start again. In other words, we don't want the plus 2 pi k part. Or the plus pi k part. The answers, if this is the way the question is worded, is just those two values. In fact, in this case, this solution doesn't help because I've only found one solution, and there are, in fact, two. So for this type of problem, this answer is not adequate. I can't combine them. I have to write them as two separate lines. In this video, so far, we've found the solutions to basic trigonometric equations like this one. In fact, this one's already in a form that we can just look up its answer in a table, or at least its principal answer. What's critical about this video or about this topic is that this is not, this principal solution, this first principal solution is not enough. Not only is there a second solution between 0 and 2 pi, but depending on how the question is asked, there may be an infinite number of solutions, and we want the most concise, compact way to write that answer. We've also solved a few equations that weren't quite ready to look up in a table. We had to do a little bit of algebra first. There's another type of equation you might run into in which you'd be required to do some algebra before you start looking for a solution in a table. And that's what we're going to do in the next video.